talupoja mõistus, common sense, very ambitious title. I think it wasn't put by Tanel Tammet himself, so that's what we expect him to talk about. He did not reject the title. Tanel has in the past studied at Tartu, applied mathematics, computer science in here, did PhD at Chalmers. Did you do postdoc anywhere? At Chalmers in Sweden. Like myself, went abroad during 1990s, so spent a long time in there. Developed some theorem provers, award-winning theorem provers. In Estonia, collaborated with Enn Tõugu at the Institute of Cybernetics, where most of Estonian IT people have gone through in 1980s, in 90s at Chalmers, and now full professor at Tallinn University of Technology, or TalTech, as well as I think works next door at Cybernetica, and God knows how many different other activities. Please, Tanel.
Thank you, and many thanks for inviting me. I've never actually given a talk here in this building, so it's my first time. Okay, so I didn't choose the title, but I think it's an excellent title. And the first part of my talk is not very technical, and in the end I go somewhat technical, but not so very much so that, yeah, as you said, talupoja mõistus, everybody should kind of understand that. At least I don't go to very complex stuff because I don't understand the complex stuff. Okay, so I'll start with a brief introduction and context. So what are we considering here? What's the more concrete theme, so to say? And then I'll spend some time on end-to-end machine learning. That is basically transformers. We have a brief look at what they can do and the counterexamples where they kind of miss the mark and what could be happening there. And then my main interest actually is in hybrid systems. So I then go into hybrid systems and I look at two different directions. First, how do people try to add some rules or taxonomies or whatever to learning systems, and then on the other hand, how to add machine learning to so to say automated reasoning proper, which is what I'm working with. So I use our project as a case study for this direction. Okay, so what do we mean by common sense? I just referred to Wikipedia. It says something vague, but you can't make it much more precise, I guess. So it's going to be kind of vague. Now, personally, I like to think about this common sense reasoning as something which should be basically grounded in something what a 2- or 3-year-old kid can do. So I don't think it's important to know about countries, presidents, restaurants, nothing of that kind. That's irrelevant. So if a 2- or 3-year-old kid can do something, then that's like the core common sense. Okay, they have some pretty good linguistic capabilities already at that age. And then there is something much bigger, which is AGI or strong AI, and I'm not going to speak about that. So the common sense thing is a much smaller, much easier part, at least in this context here. And I think nobody has any ideas how to achieve AGI. Maybe it will come, I hope so, but I won't talk about that. Okay, and more about context, it's always good to remember this slide, that we have had these famous AI winters, and the typical reason has been over-promising something. And the first winters basically came from over-promising the capabilities of reasoning systems and the machine translation systems and expert systems, which were turned out to be much weaker than what people really said they will be, right? So obviously everybody's thinking are we now at the top of a wave or going down, or maybe not? Yeah, I really don't know. So the narrow focus of the talk, what I'm only concerned with here, is just capturing meaning in natural language sentences. So generally said, common sense could mean like also pictures, walking around, robotics, autonomous driving. It's all very relevant, but it's also very complicated. So in a way, capturing meaning in sentences is it's a more narrow thing than just speaking generally about common sense. And so that's what we consider. So we want to understand what is said, we want to answer questions, we want to explain answers, and maybe also calculate plans of action. Pretty classic stuff here. And maybe the most famous success, which was widely published in this area, with understanding language, comes from IBM Watson like 10 years ago. And they actually won this competition. You probably all know about that. And here are some example questions what were asked, and Watson very quickly managed to answer. It looks that the speed was also an important factor why it won. And it's not very easy to answer these things. And actually, when you read about how Watson was made or what's inside, it's pretty widely published. So it's an interesting reading, and people talk about that a lot. So it's a huge collage of different hacks. There is no single system, no single principle. They just try to put more and more stuff in there and solve this and that question, etc., etc. And then IBM tried to use this as a marketing thing, basically saying that we are so good at AI, and they tried to actually move it to medicine and built a large group around that. And finally, it all collapsed. So I think a year ago or so, they just pulled the plug and said, we are not going to do that anymore. Nobody's using it. It's worthless. But now the people who are behind the core Watson team actually made a startup, which is trying to do the same kinds of things, but in a more modern way. And actually, our small group is moving in a similar direction. Of course, we are doing things differently, but there are strong similarities to that. Now, the very classic old-style approach, starting, I think, from actually 60s, for doing this kind of thing is that saying that, okay, you need 3 basic components. You need an English-to-logic parser to give sentences, ask questions, and then you need a logical reasoner, which based on this output of the parser derives the answers. And then you need large knowledge bases, which the reasoner can use, which contain this knowledge about the everyday world. And as generally, it's not the wrong view. But what happened was that all of these things turned out to be so incredibly hard that they all failed miserably. So nobody managed to build a good parser, nobody managed to build a sensible reasoner, and not to speak of knowledge bases. So none of this worked. So it worked like for toy examples. You certainly could publish papers very nicely, but not doing anything serious. And the most famous case study of this old-style approach is the psych system, which you probably all have heard about. It's a very old project, which surprisingly is still alive. And the guy who is one of the AI classics, Doug Lennart, is still leading it, and he's pretty active. And quite recently, he was on a Lex Friedman podcast and talked a lot about that. And who hasn't listened to that, I recommend. It's interesting, and he's also still very optimistic, and he has some interesting points there. Definitely worth listening to. Now this is typically considered to be a major failure, in the sense that they promised a lot, but they delivered little. They did manage to deliver something, otherwise the company wouldn't exist, right? It still exists. And they haven't published almost nothing, right? So nobody knows what's inside. It's a big mess, basically, what people understand about that. But we don't really know. And it was all handmade. from the beginning, over a long period of time, by lots of PhD students and co-workers. So you can imagine, during a long period, people made in hand different additions, changes, things. It has to be a mess. It just can't be otherwise. Now, slightly related to all of this is another relatively recent large project starting from, I think, around 2000, which was made very high profile by Tim Berners-Lee, who know, pretty important guy. He was kind of godfather of this project, and it slowly fizzled down. It hasn't like totally failed. It has produced some good things, but never achieved its promises. But it didn't really try to do common sense. It had much more modest goals, which couldn't really be reached, I would say. Good to know that this thing still exists somewhere. Okay, and what were the bad things about that? It kind of drifted into pure academy on one hand, and then the assumptions that people want to publish data and rules on the web never really materialized. Nobody wanted to do that. But then, as I said before, a few positive things came out of it, and maybe more. But I'm not really concerned with that. So, the next part, we'll have a brief look now at end-to-end deep learning for questions and answers in natural language. And basically, it's a very, very active field, as you know. And I think there are two main systems which people use for experimentation and research. And mostly they use derivatives of Google BERT, which many of these derivatives contain BERT somewhere in their name. So you can always recognize, but not all of them do, though. And then, of course, since GPT-3 was made publicly available by an API last year, people have started experimenting with that and building on this API. And that's also an interesting thing, but it's not publicly available. It's just the API, right? So you can't retrain it or anything. Okay, so what do we know about end-to-end learning? Of course, there is a lot of hype, especially the OpenAI people building the GPT-3 are in the camp which says that end-to-end learning is the way to go. Maybe it is. We don't really know. And they basically say that if you continue putting more data and improving somewhat on the parameters of the learning system, it can reach whatever. But so far it hasn't, but it's surprisingly effective. I'd say if you take a typical common sense oriented benchmark, and there are many, we'll look into these briefly, they get like 75% right, approximately. So it's the same with these BERT derivatives and GPT-3, that's the approximate number. So it's not very good, but it's surprisingly good, considering that it's just a transformer. You know, it just predicts the next word, knows nothing about words, just gets a lot of text and predicts the next word, or actually the token, which is a piece of a word. Okay, so here is a small example from a large superglue benchmark. Sorry, I still keep on that. Says something about the soft drink. Long story. No child would understand that, by the way. So it's a pretty complicated story. And then it asks, is this root beer a Pepsi product? And the story doesn't clearly say that. It just kind of hints that since it's bottled by Coca-Cola, then perhaps it's not Pepsi, but who knows? Maybe Coca-Cola bottles also some Pepsi stuff, but probably not. So that's what GPT-3 thinks that no, which is right, okay? And a few more very well-known examples. I think one of the most popular examples from Superglue, I think it was the first one or just an example in their paper, asking for a cause. Why does body cast a shadow over the grass? And then you get two choices. Okay, if you just ask the system to predict an answer, it's hard to measure, is it right? So it's much easier to give choices. Okay. The first choice, the second choice. The first choice is right. Okay. And then you have the open book QA, which is somewhat different. Actually, OpenBook QA has a lot of test questions, also choice answers, plus a large number of background knowledge which you can use, which are also English sentences. You can choose which one is relevant, so it somewhat helps, but it doesn't cover all the background knowledge necessary. Okay, so you have several possible answers, and these kinds of things work pretty well with transformers, but you have to build on top of that, of course, because GPT-3, well, doesn't tell you 1, 2, 3, 4. You somehow have to build something on top of that. I don't know exactly what. Right. So they get something like 75% right. Now, there are systems which get much more right, which get maybe 90%, but they seem to be not really trustworthy. So I think these results are kind of doubted. They are not built by a large group. It looks like there may be some hacks. They have been pretty clever in trying to choose something, who knows what. So these larger numbers are a bit unclear. And there are many suspicions, basically. First, well, having like 75%, maybe not really good enough, okay? Now, consider a different area, driving. You wouldn't want the car to be 75% right. No way. And that's so in very many cases. If you want to buy an airplane ticket, right, to the question answering dialogue system, you don't want it to get 75% right. So it's not really okay. And then the standard worry about all kind of end-to-end machine learning is maybe there are these superficial hints, artifacts, you know, like with pictures where it looks at the background and texture and then determines what is there and not really the content. And maybe the results are not generalizable, but they don't look like they are. And if you give a new benchmark, the system suddenly doesn't work very well because it hasn't been tuned to that, and all these kinds of things, which are like suspicions towards the really high capacity of pure end-to-end learning. Now, there is another interesting system which was published, I think, last year. It's Microsoft and NVIDIA joint system. It's much larger than GPT-3. They're not as popular, though, and they have a nice results table where they show their results without any specific tuning on a number of common sense benchmarks, or similar things to common sense benchmarks. And it looks like it's, as I said, like 75 roughly, sometimes better, sometimes a bit worse. And there are some cases where they are much worse, like there is a, second from the bottom is a Hans benchmark, which is not really a benchmark. It's a collection of adversarial examples, basically, for testing, more or less. And it doesn't require any knowledge at all, just understanding the structure of simple sentences. And there are like yes or no answers. So if you randomly kind of choose, you get 0.5. So 0.6 is not spectacularly good, I would say. And the numbers with the star mean that they are the best for this particular benchmark. Slightly best, I guess. Okay, and this, of course, leads people to the question of maybe we should need better benchmarking. There is a recent paper trying to say that, okay, we really need better benchmarking. There are these artifacts, stuff is not generalizable, et cetera, and they have some suggestions as to how to build a better benchmark. But as we know, this is really, really hard. It's not easy to build a trustworthy benchmark where you don't get these subtle hints everywhere. Okay, and now I have some concrete examples because I just kept playing with GPT-3 at some periods. And here is some examples from the Hans adversarial collection. So the Hans has this structure that there is a sentence and there is a question. and doesn't need any kind of background knowledge, just understanding the English syntax, basically. So from reasoning standpoint, it's trivial, but from parsing standpoint, it's not. But the transformers don't parse, okay? So they do something different. So that's why it's not really trivial for them. And they look at different things, okay? So and with the red, I marked clearly wrong answers, and with the green, I marked clearly correct answers. So that's what the GPT-3 told me when I asked it. These were the concrete GPT-3 answers. And I ran these on this largest model they have. And something I have not surprisingly observed that during a half year I played with it sometimes, and it changes pretty often. So it's not so that tomorrow you should get the same answers as today. It changes really often. It's not very stable. It's not bad, really, but it's good to know that it's not stable. And they clearly learn more and more. So they clearly keep developing it, okay? So it starts failing on some things it was successful before, and vice versa. Okay. Then there are some famous benchmarks again, where GPT-3 gives surprisingly nice answers to really hard questions. Like they all come from, the last ones come from Vinograd. They are actually the classic Vinograd questions. And the first ones, I think, come from OpenBook QA. So it answers pretty nicely, right? Gives a long answer, but we understand that that's really what we were looking for. And particularly the last two ones tended to be hard. Now, we don't know really that it manages to get all of these kinds of things well, and we actually know it doesn't, because it's roughly like 75% is the rough number, but in these cases worked well. And now I did some very small tests on my own, and I brought out some interesting features here. So trivial questions. Not syntax parsing, but just world knowledge. So we get sometimes surprising results, and as I said before, these results tend to change very often, actually. So some days it thinks a bottle can drink, some days it thinks it cannot drink. And we can have hypotheses why it thinks something can drink. Well, beer, well, can, maybe the can means beer can, who knows? Maybe it thinks lemonade is actually drunk like a person, but it doesn't really think. It's a transformer, it just predicts, right? Then some trivial logic things. Well, logic is not really the strong side of transformers, so this doesn't work very well. So the third one is basically transitivity, which it doesn't get here. In some cases it does. It's not like it never manages to get that, but here it doesn't. They're all clearly wrong. So here are some trivial inferences. So it's elephant's animal, John is an animal, John is elephant, is an animal, works okay. Now, you may think, which is probably true, that it has a huge amount of information about concrete words. So it's always interesting to substitute fake words instead of real words. So I did some substitutions. And then you don't really know what you get. So you might get a good answer, but not in the last case. I think that probably this adding this all had this made this butterfly effect to make it say yes. Okay, here are some exception cases. So it's you have rules like some birds generally fly, but there are exceptions. Some birds don't fly. And we don't state these exceptions explicitly, right? We just say birds fly. That's it, okay. And we should understand implicitly that doesn't mean that they always fly. Okay, and then we come to specific cases and say, okay, this specific case here Mike is not a specific case, but John is a specific case. It manages to answer okay. That's good. Now, I did some changes. Did put some invented words here, and then it became much harder. Folkamere is another invented word. So this is a bit nonsensical in the end. So why? Okay, and more of that. Now let's go a bit deeper. So let's explore the first thing. So we have John is a bird. Can John fly? It incorrectly thinks it cannot. Okay, it's a bit weird because we say most birds can fly. Maybe most isn't good enough. Then we get two okay answers, and then we get a really weird answer in the end. We explicitly say John is a bird, and then ask why he cannot fly. And it says because he's not a bird. So it clearly got confused over some words, some vectors, whatever. Then kinds of examples people often have observed that it's okay to do arithmetic on small numbers, but it's not okay to do arithmetic on large numbers. And the naive guess, which might be right, is that it has seen very many examples with small numbers. But the larger the numbers get, the less examples you see, obviously, with these concrete numbers. If you put very large numbers there, it has never seen these large numbers. Okay? Can't learn. And that would require much stronger generalization into proper arithmetic, which is obviously extremely hard thing to do. So if you think that end-to-end learning might be capable of everything, then maybe it could, but so far it doesn't. I have some larger examples also from well-known systems. Allen AI has several common sense systems built on different, built as demo cases for different methods, and they have, as one example, this kind of thing. And you see that first we say that nails are made of iron, and they should therefore conduct electricity, okay, because there is some inference here. Iron is metal, and metals conduct electricity, and some why he gives a correct statement that nails are made of iron, which is like said explicitly, but then thinks that it's not a good conductor of electricity. A bit weird answer. And now on the good side, if we say that nails are made of plastic, then it correctly says that they don't conduct electricity. Another Allen AI example, which is a bit larger, it's basically there are no exceptions here. It just says there is a circuit has components, you can switch it on. If it is on, then things start to happen, and it clearly says that the switch is off here. That is, nothing says that the switch is on. And then we have this clear statement that the circuit is complete if it has the switch and it is on, which is not satisfied. It is not said it is on. And there is some ballast. These black lines are actually not used in this derivation. Only the blue lines are, but there are quite many. And it doesn't manage to answer that correctly. Okay, then another example, I just took a very small piece of text. Birds can fly, penguins are birds, cannot fly, John is a bird, which it perfectly well could, and then injected it into ballast test. So I took some text before and around, which has no relevance to this bird or penguin thing, and this confused it. So he couldn't understand anything, and weirdly it decided because he's a penguin, which is clearly not said. Okay, so enough of these examples. Now, despite of what they can do, we clearly saw that they cannot do everything, at least so far. And here's the main question. Can we fix end-to-end learning, like transformers do? And really, nobody knows. We have no reasons to say it cannot be done, but we have no reasons to say it can be done. And I cannot bring any arguments why it can be done, except that, well, it has been doing amazing things. This is certainly true. And world is getting better, so why not? But then we can bring some arguments against, and then these are not my personal pet arguments, but things which I think people typically say when they try to be suspicious about the capacity of endless improvement in transformers. So one very obvious thing is explainability. It's not really about answering correctly, but it's just a question, can you explain the answer? And of course, a lot of people are working on that, and it is a very important subject area, and DARPA is putting money into that, but we haven't seen much success. So you can't say not at all, but not much success. At least I haven't been able to observe any. Clearly, very hard thing to do. Now, from the biology side, it's, I think, useful to think about the comparison between brains and neural networks, because people say that neural networks are like brains, which is not completely wrong. But we know that what really happens is that when you have a neural network, you have a very simple switch, basically, a very simple calculator. And the actual neurons are extremely complex things. They are basically small animals which do their own thing. I'd say you cannot simulate a cell with a supercomputer. It cannot be done. It's too complex. And nobody understands exactly how cells work. Otherwise, people would be able to reproduce and change and do whatever they can, but they cannot. They are too hard. And each neuron, which is a cell, has like 7,000 synapses. And recently, it has become pretty clear that each synapse has capacity of learning on its own. So it's massively, massively complicated stuff what we have in the brain. And by the way, I have a favorite small video clip. Can you manage to just copy this YouTube URL and play it? I guess quite many people have seen it, but probably not everybody has. So it shows some rat brain cells in a Petri dish. Just like put together, and they start doing their thing, trying to connect. So this guy walking around there is a brain cell. Okay, thank you. How many have you seen that? Has anybody? Oh, some have. Very good. So can you help me putting that back? Yeah. Okay. Then the next thing, which is on one hand not controversial, on the other hand it is controversial. We clearly know that brain has a genetic predetermined structure. That it's not like tabula rasa. And the simplest proof of that is if you look at the video of some newborn small animal. They immediately can walk. They immediately recognize their mother. They immediately go to drink milk. They can see whatever, right? They haven't had the chance to learn anything. So that is perfectly clear. Now, on the other hand, there is a controversial theory, which we don't really know. It's about language. You know, there is a famous guy, Noam Chomsky, and Chomsky's main linguistic position, with what he became famous, is that language is also mostly genetic, that we have strong pre-built structures in the brain to handle language, and when we actually learn the language, then we instantiate the learnable parts of that. But it's not really easy to test, so unclear. Maybe it is so, maybe it isn't. Okay, and the final one, this is maybe debatable. In my understanding, most of these famous landmark AI systems are hybrid systems. That is a mix of machine learning plus something else. So there are exceptions. I think that for object recognition and story or picture generation, what the transformers do, I guess there is not much of a hybrid component. But otherwise there is, like Siri and Google Assistant are very much like complex rule-based plus some learning things. Most automated driving systems do a lot of simulations and they have plans and actions for that. I'm not completely sure about Tesla. And then, of course, AlphaGo, AlphaZero, and AlphaFold contain large search engines of different kinds. They are not like things which just learned on their own. They had pre-built structures which were instantiated by learning. So the question is, if some pre-built structure is necessary, how can we get that? Well, one hypothesis is that maybe we could also learn the pre-built structure. Now, when we want to take an analogy from biology, that would mean that we would have to through learning, go through the whole process of natural selection leading to us, which is theoretically maybe doable, but I think not really reasonable to think it can be done. The world is just too complex to go through that. So I think it's much more realistic to build some pre-built structures on our own, as good or bad as we can, do that, and then instantiate these things in there with machine learning. So for example, it probably will help to have pre-built knowledge, knowing that there are objects, and that they are mostly persistent. They just don't disappear the next second. And there is something about space and time, and it has some physical properties. We roughly know how things move. Objects have some relations. We like some objects, some are frightening, etc., etc. All animals know that, right? From the birth. It's pre-built clearly. And then they start learning other things. So probably building these things is useful. But we don't know very well how to do that. And the hypothesis is that these are the results of genetic evolution. Okay, so we come to the hybrid systems then, which exactly try to do that in different ways. And basically for this common sense question answering area, it means that we want to do machine learning, but we also want to have some kinds of rules or some kind of pre-built structure. And there are basically two approaches. Well, you can put anything in between. I would say the edge cases are that you first have a machine learning model, and then you try to inject some rule systems into that, making it thus better. And this field is extremely active. And very clearly so, because we know that the machine learning field is extremely active. So why shouldn't you try to do that? Maybe you can improve on some benchmarks, and people can actually improve on some benchmarks. So it really works. Not very easy. And you can do it in gazillion ways. So there is a lot of space to experiment. And the other opposite direction is you take a rule-based system, and then you try to add machine learning to that. And of course, a few people do that, but there are much, much less people doing that, also for good reason. For example, there are very few people doing active work in rule-based systems when compared to machine learning systems, which is kind of obvious when I think about the internet winters and it all failed all the time. And machine learning stuff really worked pretty nicely. Okay, so that's what I am doing with our group, because it's much more interesting. And we have some let's say, some competence which we can put into that, which is not very common. So I'll first go into this first part to get some understanding of roughly what people do. So first you have to understand that there are immense number of possible ways how you could try to do that. There are so many kinds of rules, how to use them. Should you try to use them before machine learning, after machine learning? How the hell do you do that? It's unclear, but you can try in very many ways, and so people do that. They try in very many ways, and it's really interesting. So typically, we gain small gains over pure end-to-end transformers. Not very massive, but some. So here is one recent paper, and I can't say I understand it very well, but I try to explain the basic ideas as far as I understand. So the paper is pretty large, of course, or big or complex or whatever, but I think this is a bit understandable example. Let's try to go through that. So there is a question. What kind of store does a merchant have if the cell produce? Okay. And then there are these possible candidate answers, and market is incidentally a correct one. Okay. So now let's imagine that we have a very simplistic rule system, which is basically propositional, which is basically just triplets, which is very common. And people call these kinds of things knowledge graphs, because you have nodes clearly, and nodes represent concepts, and then you have edges, and edges give you some relations between concepts. It's an extremely common thing. And as you can see here, some of these relations are pretty long, kind of unclear. What does it mean is related to? Everything is related to everything, almost. So actually, one of these most popular large knowledge graphs, ConceptNet, contains like 2/3 of its rules are just is related to in some ways. Okay, then is that location of? Okay, that's much more concrete, but not very easy. Can't really say maybe in one word. Is used for also kind of not very easy. Okay, how do you say it in one word? Can't very well. So here you get these longer sentences. Okay, but anyway, why are these 3 boxes marked green? These 3 boxes actually occur in these questions and the options. There is a market, which is one of the options. There is a produce, which is in the sentence. There is a merchant. Okay. And let's see if there is some trading, no trading, some shop, no shop, although there is a shopping center, store, no store directly. So these appear to be more salient or more relevant. Okay. Let's see other connections between these. Okay, there are. Let's count these connections. We get some number. So we could try some other combinations of the words and see other connections. Okay, let's count these connections. So you can try very many combinations and count the connections. And now, of course, you don't have to just give a same strength to all connections, like 1, just counting. It makes much more sense to somehow try to tune this connection strength. And there, clearly, you can use even simpler kinds of machine learning, like co-occurrence or some similarity matrices, etc., etc. Many ways to do that. So this is one approach which sometimes helps. It's not everything what is in the paper. The paper is much more clever, but this just gives you some understanding of the simplest ways to try to do that. Okay, here is a kind of more complex picture which I don't really understand, but which is more or less typical of what you see in this literature. That they find out ways to use knowledge graphs typically in some parts of the learning process or answering process, and then they explain how they do that. But because it's pretty complicated how they do that, it's really hard to understand. So So you can read the formulas, you can look at some architecture picture, and if you do a lot of mental effort, you can more or less understand, but not so immediately. And now the concrete question, which you can't very well see, I copied it out in blue on the left. The question was, if it is not used for hair, round brush is an example of what? And the correct answer should be art supplies or something similar, because, okay, for painting, yeah, and round brush, maybe then not for wall painting, it gets a bit fancy here. So they also have a knowledge graph of the kind we saw before, and they inject in clever ways before and after learning and in question answering. And now they actually have results on how much they managed to improve stuff with that. And you see that this grease elm line, the bottom line, is now their system. And there are let's say, two different tables. The first one, as I understand, is done by themselves, I think. I'm not completely sure that they made this test. That they ran Aristo Robert, which is a BERT specially tuned for question answering, and got 78, and then they improved like 6%, which is not really trivial to get. Actually, it's really hard to make these numbers a bit higher. It's really hard. And the second is this known results, what people have published on the same benchmark. And you see that there are actually a bit better results. This Unify QA actually does similar kind of thing. Also uses a knowledge graph, but in a different way. Also in pretty clever ways. So they are almost as good as them, but not much better. Okay, now a few words about these common sense knowledge bases. We had the view of some examples of a knowledge graph, and go here, and another example of a knowledge graph. How they typically look like. Like you have a concept like car, and then you have edges, which normally are not single words, but small phrases. And most of the knowledge graphs, I think, contain a limited nomenclature of these phrases, but some are unlimited. In some you could have very long phrases. Stuff like that, and these are simple triplets, and there is no time, there is no change, there is no space, there is nothing like that. So it's a very simplified picture. You can't really understand how the world works if you look at that, no way. But it helps a bit. Sorry, I have to go back. So here are some of the most well-known. I just listed them. I'm not going to go through these. They tend to be very different. They are made for different purposes, but most of them have this kind of structure, that they are triplets of some kind. Maybe with a limited structure, maybe with an unlimited longer phrase structures, but not all of them. So some actually contain logic, like adim and sumo and psych are these logic-based things. And logic-based things are very hard to work with because, well, then you'd have to convert something to real logic, which we can't very well do, and then you have to use a reasoner, which we don't really have. It doesn't work very well, etc. And people are building more, but it's not easy. So I'm not going into that. So another active area, which is very closely connected to injecting these knowledge graphs to machine learning, is actually improving the knowledge graphs. And the knowledge graphs don't contain very obvious things you'd expect them to contain. Like I haven't seen a knowledge graph where you could infer that if there is an animal who has a trunk, then it is an elephant. No. there is certainly a fact saying that elephants have a trunk, but not that if you have a trunk, then you are very probably an elephant. And not that if you fly, then you're either like a bird, an insect, or some human-built flying machine. So they don't contain that. So, and when you want to get this absolutely necessary stuff out of them, then what do? So one way is try to start improving on the knowledge graphs. You could say that, okay, we have a rule that elephant has a trunk, there is only one guy with a trunk, which is an animal. So let's think that probably works vice versa too. Or if there are two versions, then generate something. This is not certain, but it doesn't have to be certain. It's okay if you have some confidence in these, okay? So you can actually start building things on top of knowledge graphs with non-zero confidence, with non-one confidences, and have some rough measure of the confidences. And this is also a pretty active field, although not as active as actually injecting knowledge graphs into machine learning. But people are doing more and more of that, because when you try to use knowledge graphs, you see that they are badly lacking. And so the obvious thought is, okay, let's start improving them, and let's see how far can I get here. And here we really get some help from different kind of statistical methods. I'm not saying you have to use deep learning here. We have lots of different learning mechanisms, and people do try these and invent the suitable things. Clearly, you can use like co-occurrences even, for example, for a lot of that. Okay, and now I am coming to this other direction, the case study of adding machine learning to a rule-based system. So I'm going a bit technical and trying to show how it could be done, or how far have we got, or what are the issues there. And there are a few groups, as I said, who do similar things. One group is the startup built by the original Watson guys. Then there is a quite interesting group at University of Texas doing very similar things, and there are a few more, but it's not a very active field. And there are many reasons. Well, one is obviously it's very hard. It's not so directly connected to machine learning. And also people don't typically have competence in these areas. So try to find somebody who can build a semantic parser. So try to find somebody who can actually work with a logical reasoner. There are very few people who actually build logical reasoners or understand how they work in serious ways, not in some simple ways. So it's really hard to get this kind of group together. And if you don't have that, then you can't get very far because some critical pieces are missing. So these three components are exactly the same as I showed you on the psych slide, or before the psych slide. So and my hope here is that the technology and theory we have now has improved so much that there is some hope of getting sensible results using this approach. So basically, I think that psych was far too early. They tried to do everything by hand and wasn't really feasible. You could get somewhere, but not very far with that approach. But I really hope that the tools we have, the machine learning tools, the data, the processors, the theory in every part, even these knowledge graphs which we have and which we didn't have before, that these can lead us to some significant improvements over the state of the art in common sense reasoning. I can't say it will certainly happen, but I'll say that there is some grounded hope for that. Okay, so I'll speak about all of these. And I'll mostly speak about the second part because that's exactly my area, what I'm mostly working on. It's taking an automated reasoner for logic and starting modifying it so that it could be used for common sense reasoner. Because if you really cannot, then there is no way to put it together with this semantic system or let's say results of a semantic parser or the knowledge graph, or you just can't get anything. Okay, so let's start briefly with the semantic parser. This is something we are working on. We already have a system which does a few things. I have some examples, not very good, but already something. And why is hard? Well, we know that first, even from the syntactic standpoint, there are very many syntactic parse trees. And there is a famous example, I go there and come back, is this: I shot an elephant in my pajamas, which you can interpret in two main ways: that elephant was in your pajamas when you shot it, or that you were in a pajamas and then shot an elephant. Okay, they are both syntactically correct. And this is just a famous example, that's why it's here. And actually, if you have a bit longer sentence, then you get the combinatorial explosion of these syntactic parses. So it's very hard to determine which is the correct parse, because this determination has to be done semantically, what makes sense. And if you don't have real semantics, then how do you do that? And incidentally, this has been one of the early areas where people tried to use automated reasoning together with parsing. There is a famous guy, Johann Boss, and Boss wrote the Semantic Parser, and then what happened is, of course, these ambiguities everywhere. And he started using automated reasoners trying to show that, okay, some of these parses were clearly contradictory, just to filter them out. Didn't get very far with that, but got quite a lot of interesting examples and theories around that. So second thing is that, okay, now objects in the sentence can have many roles. Like there's an example: man opened the door, the subject, the door is kind of object, this was opened. Then you say a key opened the door, then the key is not really a subject, but the key is kind of helper, although it's a bit of a subject, but it's not the same thing. And whenever you have a bit longer sentence, you have a lot of things like that, like Brutus killed Caesar with a knife. So knife is also something which is connected to killing, but is not a subject or object, but some kind of helper. And when you say in the agora, then that's again a place, and you can have many things there. And it's hard to determine. If you look at the syntax tree, they are not clearly distinguished. Then there is the famous thing, co-reference. Resolution, you have he and it, and not only that. You could say elephant was big, the animal went swimming. Also co-reference, although there is no he or it. And then the question really concerning knowledge representation. Well, we know there is context and space and time and all these things, and how do you really represent it so it's usable? It's really hard. Okay, so semantic parsing now means not this syntactic tree building, but trying to build some kind of conceptual picture or conceptual semantic graph. What does it mean really to be semantics? Very unclear. So people have, of course, invented different frameworks for somehow encoding the semantic part. There are quite a number of these. Some are more well-known or studied, and most of them have parsers. And we incidentally tried out a lot of parsers and investigated their examples. And they all kind of worked for their examples, but they didn't seem to be usable for our purposes. None of them. So we were really like unhappy about that. So I was surprised. I thought there are much better parsers available, but there weren't. And then I talked to people who actually built these parsers, several of these. And they said, yeah, that's the case. We don't really have seriously usable parsers for common sense kind of thing. So they do some things, and that, but not very far. So you could think maybe we can connect these, which could work, but I don't know. So what we did was finally give up and took the approach that let's try to do it ourselves. So this is one of the lines of work we are currently doing. So we took, the approach we took was we took the stanza parser from Stanford. You probably know the big famous Stanford parser. Stanza is a newer version of that, which is in Python. It has the Apache license, incidentally. And this is able to build these classic syntactic trees, which are called constituency trees, and also these universal dependency graphs. And the universal dependency graphs are much more complicated than constituency graphs. They have much more concepts or H names. But on the other hand, they are much more fine-grained. So you can actually get quite a lot of semantic information out of that. It clearly distinguishes whether something is a subject or object or a helper thing or a place or whatever. So it's really helpful. And to get the correct parse, Stanza uses machine learning on labeled sentences. So it's a clear example of using large labeled data to get a good parser. And in my experiments, I would say it's roughly like 95% correct. So on Hans examples, it's more or less 95% correct. So I'll later show you how I know, which is pretty good because there are so many different parse possibilities. So it just gives you one parse and says, that's it, and then say roughly 5% times it's wrong. Okay. So what do we do with that? We get the stanza output graph, and then we convert it to first-order logic, really classical first-order logic with quantifiers and everything and all the stuff, and we extend it with confidences and exceptions. So things are not certain, and things can have exceptions. So it's not strict. It's not like yes or no, okay? So now coming back to automated reasoning. So this, it so happens, is my core subject, which I worked a lot on, but at some point in time, I didn't want to work with that anymore because I didn't see clear applications which I was interested in. But I came back to that like 4 or 5 years ago because I started believing that the current tech and theory what we have in language and machine learning really could help us use these in hybrid systems in a sensible way. Now, most of the work in automated reasoning, now what's automated reasoning? It's the main standard thing is that you take some problem, let's say mathematics, verification, or even some language semantics, something like that, you encode it in first-order logic, and then you run the prover, and the prover tries to prove it. If you're lucky and it's true, it could prove it. And we know because of completeness, if you have infinitely many time, infinitely large memory, eventually it will do it. But it's undecidable. And that means that if it's not provable, then it will typically not terminate. In simple cases it could, but mostly it doesn't. Now, there are other forms of automated reasoning, of course. You probably all know about Smt solvers, and Smt solvers are like the midpoint between propositional logic, which is solvable, and first-order logic, and it's basically built by taking propositional logic stuff and adding decidable first-order logic theories on top of that, like restricted arithmetics and things like this. And these are really practical things because they can be used in verification. But the general first-order proving, which takes like full logic, where people can use it, basically in 2 directions. You can do some verification where Smt solvers work best, and you can extend and work on that, and that's really, I think, the main application here, which is hard. And then people work on improving it for mathematics. And some of these things, what they use for mathematics, are used in interactive theorem provers, like Lean and stuff, and Holl and Isabel. Okay, and then, of course, most people in the area, or in this research area, do just research in logic. So they are logicians, they do mathematics, they find some interesting theorems, prove something, cool stuff, but they don't build systems. And very little effort has gone to automating anything like common sense. It's not at all mainstream. So there are no systems for that, more or less. And now how we build our system. First, I built a classic first-order reasoner called GKC, a horrible name. It has complex meaning for its words, not just graph knowledge, but many other associations, which I won't go into. And this is a pretty good prover. Classical prover, not really the best. Below here is a very recent competition of these provers, and I'd say all serious provers are there. And the first ones are vampires, different versions of a vampire prover. And then you have E and CSE, which is basically the same core as CSE, is a slightly modified E by a Chinese group. And then there is an I prover, which is a separate thing. And then comes my JKC, which is roughly the fourth. And another interesting thing is that these first three have been, I think, no, not first three, but Vampire and E have been the best for 20 years, almost 20 years. My own very old prover used to be top prover for like 3-4 years in the end of 90s, until I got bored of that. So there is some progress, and actually the people working on Vampire and E are improving it in very interesting and clever ways. But it's a very small community actually working on these in serious ways, and it's very hard to be better than Vampire, say. It's like extremely clever, complex stuff, improving all the time. Now, one of the ways people improve on these is doing different kinds of statistics and machine learning for determining optimal strategies. So the main game has been for the last, I think, 10 or 15 years is finding interesting and suitable combinations of strategies. So you run a prover with very many different strategies over and over, and you try to combine these. It's not like some logic thing. It's very fine-grained stuff here. So people do active research, and the main group doing active research in machine learning is in Prague group, and they are working on the MESAR system, which MESAR is a large formalization of mathematics, and you have a stable large set of theorems, and they can do something similar to what you can do for language there. And the goal is to find better strategies or better guidance for proof search. Okay, now note that, as I said, since finding a solution is semi-decidable, clearly it's the complexity of finding a proof is over any complexity class. Semi-decidable is worse than anything. And actually, even very small problems can be extremely hard. So it's not easy. Now, what do we need to take some sensible steps towards common sense reasoning? Lots of things. So we need to find answers to questions, not just prove true or false. We need to survive contradictions, like you say, John is a bird. Then you say, John is not a bird. Well, in classical logic, that would mean there is a contradiction. Now you can derive anything from that, whatever. Okay, we shouldn't do that. So we should estimate confidences because things are not certain. Then there are exceptions. Then we should handle analogies. We should manage context, blah, etc., etc. So quite a lot of stuff. So we are meticulously working through that, trying to get to good enough solutions in all of these. So I'll briefly first speak about confidences. What do we do there? So let's consider some practical context. Again, a natural language question answering dialogue. So we want to use automated reasoning there. Okay, now what happens is most facts and rules are typically uncertain. Some are like more certain, some less, but we don't really know the probabilities. You can't say that I know the probability that when I go to a bus stop, the bus will come in 5 minutes. Well, I have some estimates maybe, but I don't know the probability. Maybe there is no probability really, because it depends on a moment in time, etc. So using real probabilities doesn't seem to be realistic. And what do people do? So first, when you consider probabilities, there are very many interpretations of what probability means in philosophy and mathematics. And so one of the famous interpretations, which is like the edge case, is fuzzy logic, and this is pretty popular. And fuzzy logic is relatively well integratable ordinary logic because it has this min and max operations. The nasty thing is that it's very different from ordinary probabilities in the sense that you cannot accumulate anything, it just computes a min or max. Okay, so we don't do that. So when you don't do that, then what people have been doing, there are some programming tools for real probabilities. What we don't do, then there are Bayesian networks, the famous mechanism, but works for propositional logic. Then there is logic programming with probabilities, and the nice system called ProbLog. What they do is grounding. That is, they take first of the logic formula and they put constants in there and make a large propositional formula out of that, up to some limit, because you can't ground everything. And then they calculate probabilities, and then it's Markov logic network, which also does grounding. And the example here is what they can't handle. So you have very simple logical formulas say that P of A, okay, P of I of A of B, I is like implies, right? You encode propositional modus ponens here, basically. And you say, okay, if this implication and X and then I, okay? And then you ask B, which should be derivable, and obviously is, but they just loop, because they start grounding and the grounding fails. That's it. So when you have function symbols in any non-trivial way, then they are done. Okay, so we can't use these. Now, a few words about sources of confidence. So where do we get these? So we could get them from crowdsourcing. ConceptNet has a few confidences. People just say their numbers. Then you can scrape from web and give some numbers there. You can machine learn, and this might give you some confidence numbers, lots of different ways. They are not exact, but they are something, okay? So technically what happens is that when we start using confidences, we need to have our rules, which we call clauses, and you give each one a confidence, and we also give a list of clauses from which it is derived, so that you know the sources. So you always operate with these. So these are the dependency lists, and they are important for estimating the cumulated confidence. I'll come to some small examples here. So, and what does it mean to say that you have some confidence in something? The semantics really is that we give the lower limit of the probability. That we say, well, it could be higher, but it's not less than that. And it also says that these statements support that. Okay, and the statements are from which you derive it. Example like here. You have fact that everything is a bird, but with a very low probability. And then you have two facts saying that A is a bird. Different people said that. Maybe John said one and Mike said the other. And they estimated the confidence that A is a bird. Maybe they didn't see very well. And then some other guy, Eve, said that, oh, I saw this thing. It's not a bird, but I'm not completely sure. But maybe it is not a bird, so it's 0.3. And they have all their reasons, which are in these lists. But let's say the lists are independent. Then we can derive a number like this. Okay? Basically accumulating the positive ones and subtracting the negative one. So that confidence 0 doesn't mean it's wrong. In our interpretation, it means it's unknown. We have no grounds for saying, is it true or false? Just no information. And when you want to say something is wrong, then you give a confidence of a negation of this thing. That you have grounds to say that the negation holds. So what do we do there? So we process these problems like that. So we do ordinary search, but then we throw away all contradictions which don't contain answers, or the actual question, let's say. If the question is not inside the derivation, we just throw it away. And this way you just get rid of contradictions, and it's actually complete. So we don't ever stop the proof. We just run the prover until a limited time is over. So let's say I give it 1 second. then it maybe finds 5 different ways to prove that A is a bird. But it may have different grounds for that, different things, rules or facts it came from, and different confidences. And then we can cumulate or subtract the negative things. Okay, so we also try to find explicitly a negated fact. So first we try to prove, okay, is A a bird? Maybe we found some proofs. Then we try to prove, is A not a bird? And maybe we can find some proofs for that as well. And then we combine these. It's pretty straightforward. And the time limits here are crucial. So, well, obvious thing is to give half of time to positive search and half of time for negative search. If you give more time, well, you might get more answers. So it's not certain what you get. It's really not stable. It depends on time and your search strategy. And you could say optimistic approaches give more time for positive search and vice versa. I won't go into that. So a simple example, we have a bird, Tweety, with confidence 0.8. Then we say bird can fly. If it can fly, it's fast, but not completely certain. There's some confidence numbers. And then we say if it's fast, if we find something which is fast, that's the answer we're looking for. So obviously we can derive that Tweety can fly, and we just multiply. The standard thing, you multiply. And if they're independent, the multiplication is okay. If they are not independent, it underestimates the probability or confidence. And the cumulative confidence is a bit more tricky. We have this standard formula for probability of A or B. You have to add these and subtract them, the multiplication, and we estimate this independence. The whole question is, are these statements independent? Thing is, you can derive something from the very same rules or same facts twice, different ways, and these shouldn't cumulate. So we have to somehow estimate how independent they are. So we have a measure of this estimation of independence. And then we have a formula which uses this estimation of independence and the overall rough estimation of independence. And this, in one edge case, if everything is independent, it's just the same formula we had before. You add these and then you delete the multiplication. And if everything is dependent, then you just take the max, like you do in fuzzy logic. So these are the edge cases, which seem to be pretty sensible edge cases. Okay, here is a small confidence example. You have the same thing, but you then also say something. You say something is in air, and if it's in air, it's also fast, and then you can say that, okay, you got answer with 0.5, and then you got answer with 0.72. And then you can combine these to get the higher answer. And now you can see the edge cases, what the edge cases would be here. Okay, we used some examples from these systems, Problog and Alchemy, in comparison, and they do grounding, so they can't do our examples, but we can do theirs. And I skip over the negation examples and go to some simpler things. Again, a classic example, social network. Really naive, but it's a nice example. And we see that the numbers we get are not the same. They are similar. And actually, all the systems get different numbers. So they don't get the same numbers. And another classic earthquake example, again, what you have to look at is the confer numbers, and then the Problog numbers and the alchemy numbers. They're all slightly different, but not totally different. The confer plus is the positive arguments, and the confer minus is the negative arguments, and the confer simply is the sum. I skip over that. So the last part, or almost the last, is handling defeasible reasoning, the next thing. And what that means is exceptions to rules. That's the classic penguin case. Birds typically fly, but penguins don't. So can I handle it with confidence numbers? Not really. Because, well, you could say that the probability that bird flies is not 1, but 0.95 or something. But the thing is, penguins form a very large subset of non-flying birds. So it all makes sense in the probability theory way, but you can't just multiply and add here. So I have a small example of real natural language input and output our system can currently do. It can parse it. It's not very hard to parse, build the logic, do derivations, convert derivations to English. So the blue stuff is what our system actually says. And I just tried out with GPT-3. Should work pretty well on this example. It's not exactly the same what it said. It didn't give me all the answers. Okay, my system gives all the answers. Up to some number, of course. It can't find all if there are very many. The last one is a bit weird. I just asked, can it swim? There is no information about swimming whatsoever. GPT-3 somewhat thinks that if she's a bird, it can swim, but it said it's bird, so it got confused maybe. And we have explanations which we generate from the proofs. English explanations, that's a lot of technical work to make them nice, but quite doable. So we can explain stuff. The bit more complex example, which is basically what we saw before. So it can answer these things also. So it can really parse it, really build a logic and really derive and do everything. And it just doesn't always say no. If you flip the switch, it says yes, etc., etc. It really works correctly when you try all the combinations. So how about these exceptions finally? The standard example of default logic is like this. So you have that penguins are birds, they don't fly. And then you add the default rule that if something is a bird, it typically flies, except when you can prove explicitly that it doesn't fly. Okay. And this makes this whole logic non-monotonic. That is, if you add now some statement that, okay, this guy doesn't fly, then you can't derive, or let's say you add a statement that's a penguin, yeah? Then you can't derive it flies. Before you could. That is, if you add stuff, some things which you could derive disappear. Okay. So we have a way to encode this with special literals. We call blocking literals, which contain priority information and something which has to be checked. And so when we try to prove some goal, find some X who flies, then the prover keeps on running, just as we do, for some time, and produces maybe different answers, like in this case, B, which is a bird, and P, which is a penguin. And then this P thing contains the blocker. And we have to explicitly check, can we actually prove that P doesn't fly? And we can, because it's a penguin. And so this is discarded. So that's the approach. We generate a lot of positive results, and then we start discarding these. And now this has to be done recursively, because these checking proofs can also contain blockers. And when you check these, they can also contain blockers. So what do we do? It's circular. So how do first these existing systems do? There are ASP systems, the answer set programming systems, which do the grounding, which we talked about. They build a large ground formula, which is propositional, and this is decidable. So they can work nicely with a decidable formula. But the problem is that whenever there are function symbols, whenever you have many constants, whenever you have really transitivity, they break. They don't break, but they never stop. They just give up, more or less. So you can't really use them for non-trivial cases. So our approach is to simply accept that the reasoner is not omniscient, that it cannot solve everything. We just have to accept that. And so we avoid grounding and we delay this checking, just as I explained. So we produce candidate proofs and then we filter out these things. And the overall algorithm is like that we calculate positive evidence and then we calculate negative evidence. And for positive evidence, we collect as many proofs as we can in a certain time. And then we start trying to see whether some of these are blocked and filtering them out. And we do this recursively and simply with the diminishing time limits. So the time gets smaller and smaller and smaller. And eventually we have some threshold, currently like 1 millisecond, and then we say we don't prove anything. So that's it. So you get shallower proofs the deeper you go. But it seems to work out pretty okay. And then we combine this with negative evidence because we have also the confidences, which is interesting because you have like, if you are not completely certain something is blocked, maybe it's like 0.6, should you block it? Here you have like numeric confidences and discrete exceptions which are combined. So our approach is just take arbitrary threshold like 0.5, but maybe it can be improved some ways. Then we run into the thing of priorities, which is really important, it turns out. It's that these rules with exceptions which speak about more specific things should take precedence over more general things. Like we know that birds are physical objects, but physical objects typically do not fly. Now birds typically do fly, but penguins, again, do not fly. So you could have several levels of abstraction, right, with different behavior. And the lowest ones should be preferred. So we encode this priority information actually in these blockers. And we currently use WordNet taxonomy simply to decide whether something is known to be a subset. The WordNet taxonomies work pretty nicely, but they are not really enough. We have to have a real list of words. Here is an example. So this first case, like physical objects cannot fly, birds can fly, blah, can be easily solved with taxonomies, but then you have like baby birds cannot fly, and this is not a taxonomy thing. It's more like an additional property. Maybe you say tiny birds cannot fly, or striped red birds cannot fly. Again, a subset. So it's not simply just one taxonomy object. You have to have a lexicographically ordered list here. But it works out, so you can do that. So I'm going over this slide. This basically says how you have to change internally the first order logic prover to make it work with these confidences and exceptions in addition to the overall algorithm. I still have a minute. So you have to change some things. Otherwise, you just lose completeness. It's not very complicated, not trivial either. It means you cannot just take an off-the-shelf prover and run it. No way. You have to change it quite significantly. I jump over these things. Okay, then the things we are starting to work with is analogical reasoning. It's similar to defaults in some ways. So you say you have a Queen Mary, kings are rich, king's a male, queen's a female, and then you say queen is similar to king, okay? And then you want to ask, is Mary rich? Should be. Want to ask, is Mary male? Should not be. That means when we have similarities, we really need some exceptions here as well, saying that, okay, in these and these aspects, they are not really similar. Otherwise, you start getting stupid answers. So we're right now going into this, how to do that. So I won't have time to go into our work with knowledge bases, but yes, we do that. So finally, there is some work to do. There is some theory, of course, which we'd like to work on a bit on completeness questions, considering reasoning. And then in practice, we have very many things to work on. Like, I'd say the main question is, what are the best or sensible ways where you can use machine learning and also research in NLP to all these processes? So there are some things we know can be done and we should do these, and then there are things we don't know about, and there are very many interesting questions. So if anybody is in any way interested in looking into this, we'd be very happy to cooperate. Okay, so I think my time is up.
We hope to have some questions as well. Please.
So I have a question about kind of introducing context into this formula in a sense. So you said it was also one of your future research directions. So far, I have worked with knowledge graphs. They don't capture context. You try to capture these kind of generic concepts that are kind of time, location independent. And you also brought this problem out that when in English parsing, you have this problem that English language or natural language at all is very context dependent. You can't really well capture location, time, and so on. Do you think this it's kind of possible to kind of enrich this information with context and because if you add context, you kind of lose this ambiguity. If you take context, if you go into a specific context, you know what that word means in that context. And my other question is, in my field, in the kind of enterprise modeling, there's this domain-specific modeling languages. Do you think that these knowledge graphs could also be kind of domain-specific or context-specific? For example, you make knowledge graph in a business management scenario, and there, let's say, one term means one thing, and you will have less ambiguity, and you have more confidence into what something means.
Yeah. Of course, the work people have done in these especially constructed languages, like this, can't say the name. Well, there are some people at Tartu who have been working with this, and we are not really into this. So I'm more about doing general common sense reasoning and trying to find out what the context and time and stuff is. So I'm not really looking into these constructed languages seriously. And considering how to handle all these context things, there are, of course, people have many ideas. And one of these is that you could tag your facts or rules with some context, and you could give saliency or probability depending on the context. So you could have like 10 tags to a rule of fact. This context, that context, that context, and it could have like saliency from like 0 to 1, right? So in some context, not true at all, in some context like 0.7, and then you kind of average your current thing and you find out how strongly the tags are connected. So that's something I imagine, but we haven't really worked on that, but we are trying to think in that direction.
I have a simple question. What are the development tools? Are you writing it in C, Python?
Right. So the prover is written in C, pure C, but all the other stuff is written in Python.
So machine learning approaches for NLP typically don't work with words as the basic representation anymore, but they tokenize into slightly smaller subpieces. Is there any, would there be any point to do this for your work or related work as well, that you're not using, or what is the underlying representation that you actually work with in such a text basis?
I work basically with words.
So if there's all the different forms, you have to do stemming, or you lose information?
Yes, so we basically, what happens is that Stanza already does lemmatization, obviously. And it gives you also an error result and some other things, the time and things. So we just take this data. We take lemma as a basic thing, and then we take the time and error stuff as additional. So the core thing is a lemma, yeah.
And one more, so is there lots of logic programming kind of approach? So what's the relationship to inductive logic programming, ILP kind of machine learning approaches? Is that ILP being used in the similar context? Or
I wish I knew.
Okay.
I don't know really.
Johan.
A question about, you said there are time limits on the prover. So how can you comment on the stability of the results? So if you give it twice the time, will it yield the same answer, or what?
Well, the answer to such questions is always it depends. So these examples we saw here, these are all actually decidable. So they are done like immediately. So like 0.1 second, they're all done. So that's no question. But if we have a bit larger problem, then of course it starts to depend.
Did you attempt any of these Watson, the competition, the similar questions that Watson was answering? Can you do anything?
No, not really. We are not there yet. So But what we can do is we can, as I kind of inferred, we can do 95% of hunts. That's the thing where the transformers basically do a random choice. But that's because of a stanza parser, which we then correctly convert to logic, and then it's trivial.
So use confidences as kind of lower bound on the probability in a way, or?
Yes, I wouldn't really use the word probability because, you know, it's a big can of worms. What does it really mean? But more or less, yes, it's a lower bound.
Can it happen that kind of through multiple steps of reasoning, you just kind of too quickly run out of confidence? So just by lower bounding, the lower bound is non-informative.
That's a very correct remark, because when you just do modus ponens and you start deriving things using rules, and the rules, let's say, are below 1, then it gets lower and lower. Absolutely. It gets low quickly. And that's, I think, a reason why people are not genetically built to do long derivations, because everything is so uncertain, and long derivations inevitably lead to very low confidence very quickly. So no point in doing that. So that's good in a way, because you don't do long derivations.
Okay, but I'm very confident that everybody wants to do the next quick step and get to the coffee.
Thank you. Okay.